Okay, we continue our seminars. And today our speaker is Professor Vincenzo Ferone from Napoli. He is a representative of strong Napoli School of Geometric Methods in PDEs and calculus of variations, and his topic is symmetrization methods for local and non-local operators. Please.
Okay. Thank you, Alexander, for your introduction. And thank you especially to you and to all the organizers of this seminar for inviting me to give the occasion to give a seminar in your university. So unfortunately, it was not possible to come, but I hope that in the future something will be better. So I am going to talk about some results about symmetrization methods applied to various kind of operators. And in particular, my goal is to arrive to describe some applications to non-local operators, which are operators like the S Laplacian, the fractional S Laplacian operator. And in order to describe the results, I would like to make some little introduction on these methods to explain how do they apply in the local case and how these methods can be successfully applied also to non-local operators. So let's start with this very simple and basic definition. What I mean by symmetrization? I mean, okay, the simplest way to symmetrize a function is what I will call Schwarz symmetrization, and it consists in taking an open bound set of Rn, and we say that E sharp is the Schwarz symmetrization of E, and it is defined as the ball centered at the origin, such that the measure of the ball E sharp is equal to the measure of the set E. This kind of symmetrization can be used in order to understand, for example, the isoperimetric inequality, which states that the perimeter of a set E controls the measure of the ball E of the set to a certain power with a certain constant. And using this Schwarz symmetrization, one can write down this inequality as an inequality among perimeters. So the perimeter of E is greater or equal than the perimeter of the symmetrized E, so E sharp. So this operation as this symmetrization as the properties that transforms E in a symmetric set, the most symmetric one, leaves unchanged the area or the volume, or in general, and the perimeter decreases under symmetrization. These kind of operations can be, these kind of properties can be obtained also with different symmetrization. I will concentrate on Schwarz symmetrization, but sometimes it can be useful to use also what is named the Steiner symmetrization, which consists in Schwarz symmetrization, to apply a Schwarz symmetrization fixing one or more variables. So for example, if E is a set of R2 and we take a line R, so the Schwarz symmetrization of E with respect to this line R consists in transforming the set in another set, E tilde, following two rules. We take E tilde intersect S empty if E tilde intersected S is empty, where S is any line perpendicular to R, and then E tilde intersect S is a line segment on the straight line S centered on R with the same length as E intersected S. So this means that we fix R and we symmetrize any intersection of the set T in the sense of Schwarz. So any intersection here is transformed in a ball, which in the case of in R2, this will be a segment centered on the line R. Obviously, this kind of symmetrization, so kind of partial symmetrization, can be applied also in the case where instead of R2, we are in Rn, and instead of a line, we have eventually an hyperplane. So we fix more than one direction, then we can symmetrize with respect to fixing this line. So also standard symmetrization has properties which are similar to the ones I have shown for Schwarz. So it transforms E in a more symmetric one, leaves the area unchanged, the volume unchanged, and the perimeter decreases under symmetrization. And as I said, in any dimension, we can do this with respect to a line or with respect to eventually to an hyperplane. So what I mean by symmetrization of a function? So symmetrization of a function is related to the fact that we symmetrize, in the sense I've said before, we symmetrize the level sets of the super level sets of the function U. So take any function, measurable function defined on omega, and the Schwarz symmetrization of F, sometimes I will call it spherically symmetric decreasing rearrangement. I will denote with F sharp. So it is such that its level sets or super level sets are balls centered at the origin, having the same measure as the corresponding level sets of F. So this means that if I take the level sets of F sharp, they are obtained as the level sets of F, the modulus of F, sharp. So we symmetrize level set. So in the figure, you can see some level sets of a function F, which are symmetrized, and then we build up F sharp, as I told before. So in some sense, we have we can say from the point of view of the subgraph of F, that the subgraph of F sharp is a kind of Steiner symmetrization of subgraph of F. So in some applications, it is sometimes useful to introduce the decreasing rearrangement of F, which is a function of one variable, and it is such that F sharp is equal to F star, so star stays for the decreasing rearrangement, computed on the volume of the ball of radius modulus of X. Omega n, X to the power n is this volume, and omega n, here it is missing, but it is the measure of the unit ball in Rn. So it is not difficult to see that in a certain sense, which has to be a little bit more precise, but roughly speaking, this function F stars is nothing else than the inverse function of the distribution function of F, where mu of F is defined as the measure of the level sets of the function F, of the super level sets of the function. So in view of this, in view of the fact that these level sets are, this function mu is this measure, F, F sharp, and F star are equimeasurable. That is, if I compute mu of F, mu F sharp, and the mu of F star, they are the same. And in view of this, if I consider the norm in LP of a function F, it stays invariant if F, I compute the norm of F in LP, the norm of F sharp in LP of omega sharp, the norm of F star in LP of 0 measure of omega. F star, by the definition, is defined in the interval 0 measure of omega. So these very simple properties, these very simple definitions imply a certain number of properties. And among these properties, I will quote some of them, which are relevant in the application. One of these is the fact that if I integrate F on a generic set E, E is a subset of omega, then this integral increases when I rearrange F in a decreasing way. This inequality is quite obvious in the sense that F sharp concentrates the biggest value in E sharp. So this inequality is quite immediate. I also observe that if I integrate F sharp on E sharp, by the definition I've given before, this means that this integral can be also seen as the integral of the one-dimensional function F star between 0 and the measure of E. Then another important inequality is the so-called Hardy-Littlewood inequality. And this says that the integral of over omega of F of the product of F and G increases when you rearrange F and G in the same way. So when under the integral there is F star and G star on the right-hand side. And decreases when you perform a dual operation on the symmetrization, in the sense that on the left-hand side I have the product of G star up and F star down. And F star is what is known as the increasing rearrangement, and is defined as F star down equal F star up of omega minus S. So obviously one can also define the increasing, the spherically symmetric increasing rearrangement F sharp down in the same way, and the inequality by the Hardy-Littlewood inequality can be read by using F sharp. So the integral of F times G can be read as the it's less or equal than the integral of F sharp G sharp up both parts, both terms, and on the left hand side the similar inequality. This will be useful in some application which I will show below. Then going back to the equality I have described before concerning the norms. So the norm of two functions which are equi-rearranged, which have the same rearrangement, are the same. So obviously if F star is less or equal than G star, then the norm of F is less or equal than G star. So this comes immediately. Now there is another way to estimate, which is not pointwise, as in this case, which says that if I know that the integral of ball centered at the origin of F sharp is less or equal than the integral of G sharp, and this kind of inequality I will call some concentration comparison between F sharp and G star, and the F sharp and G sharp. And this also for every BR, for every ball, or equivalently. This can be written also in terms of the rearrangement, not the spherical one, but the rearrangement first in G star. Then from these two inequality, we can also deduce that f, norm of f in LP is less or equal than the norm of G in LP for any p between 1 and infinity. So this inequality sometimes is useful to show that even though one does not have a direct comparison between rearrangements, if we have this kind of inequality, in any case, we can obtain a sharp estimate of the norms. So let us describe another property of rearrangement, which is known as Polyazzigo inequality. This states that for function with the compact support, W1P over N, the energy decreases under symmetrization. So if I compute the integral over all Rn of grad U to the power P, this is greater or equal than the grad of U sharp to the power P.
I'm sorry, it is essential that non-negative.
Yeah. It's essential non-negative. Yeah,
okay.
yeah. You can, if you have a non-negative, if you have a function which is negative and positive, then you can go to the modulus. So in any case here, you have the rearrangement of the modulus essentially. Okay, I didn't say that, but there are some ways to rearrange functions saving the sign. So, but in what I am saying here, I will never change the sign. So, I mean, I will take the rearrangement by using the modulus. So, non-negative here is just to say that U sharp is in any case a positive function. So if the equality holds, this is an observation which can be done essentially in all the inequality I have stated before. There is a kind of uniqueness, and in this case, one can say that if there is equality here, then U is equal to U sharp under the additional assumption that the level sets of some levels, the sets where U is constant, where the gradient is equal to 0, has to between 0 and the sup of U has to have a measure 0. So otherwise you can move the top of the function, destroying the symmetry of the function and leaving the equality here. This result can be found in Brothers and Zimmer in the paper by 1988. Okay, in some sense, this plays a role, in certain sense, can be used as an instrument which is kind of inequality like for the isoperimetric inequality, states that leaving the distribution function of U fixed, then this integral goes down. A little bit like for the perimeter, some quantity depending on the measure are fixed, and then some quantities depending on the gradient go down. The fact that this holds true is quite simple to describe. When you have a generic function, you can have some oscillation. So when you rearrange U, then U sharp as the minimal oscillation, possible oscillation, and then in this sense, this inequality can be justified. Okay, there are, just to understand how this works, I can quote some very classical application of this Polyazzigo inequality. One is the conjecture by Saint-Venant about the beams with the cross-section of fixed area. And the conjecture proved by Poglia says that the circular cross-section has the greatest torsion rigidity, or the Lord-Rayleigh conjecture concerning the elastic membranes and the smallest principal frequency, which is achieved for the circle, or the Poincare conjecture concerning the electrostatic capacity, or also this Pauli-Ziggo inequality has been used by in some papers in order to obtain the best constant in Sobolev inequality. And the Pauli-Ziggo inequality is used to reduce the problem to a one-dimensional problem. So, for example, for the smallest frequency, one applies Pauli-Ziggo inequality by simply observing that let psi be an eigenfunction for with the eigenvalue lambda 1. Lambda 1 is first eigenvalue. Then lambda 1 is characterized by the minimum of the Rayleigh quotient. This is realized by psi, and then at this point we go down with the Pauli-Ziggo inequality. The numerator goes down, the denominator stays fixed, and so being for the ball the first eigenvalue at the minimum of this ratio, then we go down with the lambda 1 over ratio. And so this chain of inequality gives you the required property. The last inequality concerning rearrangement, which I would like to recall, is the Ritz rearrangement inequality. And the Ritz rearrangement inequality states the following. Okay, this I am referring to this statement, which can be found in a paper by Almgren and Lieb, which is quite general, and I will use the following. So I have chosen to write down in this general form. Take a function f which is 0 in 0, and which satisfies this inequality. This inequality actually means that the second derivative of f with respect to u and v is greater or equal than 0 if f is irregular. But if f is not regular, okay, if you cannot do the second derivative, you can use directly this one.
I'm sorry, it is inequality type of convexity or not?
Well, it is the second derivative with respect to u and v. So
no, чуть повыше. Вот.
I will show one function, typical function. If u times v.
Plus, more,
нет, Юр, это не выпуклость.
Какая-то вот условие, я не пойму.
Нет, это совсем не выпуклость.
Хорошо.
Окей.
Примеры привел, ладно, хорошо.
Continue.
Okay, if f and g are non-negative measurable function, then we can say that the double integral of f, capital F, combined with f of x and g of y times w ax plus by is less or equal than the same quantity, but computed with the f sharp instead of f, g sharp instead of g, w sharp instead of w. And the similar inequality holds true for the f computed in f of x, g of x, and correspondingly f capital F of f sharp, g sharp. So this inequality is, for example, applicable to the case f capital F is equal u times v. And if I use a equal 1 and b equal to -1, the above inequality reduces to the classical Ritz inequality, which says that if I take the convolution of W with G and then I integrate a function f, then this inequality, this quantity goes up when f, W, and G are rearranged in a decreasing way. And with this choice of f, the second inequality is essentially the one which I have discussed before. So it is this one. In particular, I would like to mention that I will use this later on. So please recall this condition which I have stated here. So let's see how this instruments, these methods can be used in order to estimate solutions to local problems. And I start with the very classical problems, the homogeneous Dirichlet problem for this equation, for this elliptic equation. Aij satisfies an elliptic condition. And a classic result, which maybe is classical in some sense now, is that the solution to the first problem can be estimated in terms of the solution to the second problem, which is the symmetrized one, where the elliptic operator is substituted by delta. So this means that Aij is substituted by delta ij, f is substituted by f sharp, omega by omega sharp. And then the following inequality, u sharp less or equal than b, holds in omega sharp. This inequality can be also read as u star less or equal than b star, if I recall the decreasing rearrangement. And so this means that among all the problems in this form, the one which realizes the biggest solution in the sense of this inequality is the one which is written here. The operator has to be delta, and the datum has to be rearranged in a decreasing way. This result may be one of the first results in this direction is in a paper by Weinberger.
And this for measurable, all measurable coefficients are.
Yeah.
For all.
Yeah.
Okay.
Yeah. And in this form, it is clearly stated in a paper by Talenti from 76. So once we have this inequality, because of the property of rearrangements, any norm of u can be estimated in terms of any norm of v in a very direct way. And I have to say that also the energy of u can be estimated in terms of the energy of v. I will come back on this later. And finally, I have to say, I have said the f in LP for suitable p. Actually, we can take also f in L1. There is a way to define solution also in this case, and to obtain this kind of results also for very weak solution, for under very weak condition on them. So which are the main ingredients of the proof, especially those contained in the paper by Talenti? First of all, we integrate on the level sets of U, then use Gauss theorem, co-area formula, isoperimetric inequality, and the properties of rearrangements. So very quickly, let's see what are the main points. We integrate the equation of the set where u is greater than t. We integrate f. Then we integrate the elliptic operator. By using the Gauss, we can reduce this integral to the integral of the boundary. Ellipticity gives this inequality, and then finally Cauchy-Schwarz gives that this integral is greater or equal than the ratio between these two integrals. For the sake of simplicity, I've taken all data regular and f greater or equal than 0, then u is greater or equal than 0. So everything is has to be appropriately well justified in general case, but essentially the proof goes like this.
Вы пропустили там лямбда, лямбда.
Excuse me?
Вот так. Почему вот больше ellipticity then?
The ellipticity here.
Лямбда.
Yeah,
Какой лямбда?
One was one.
Вы ellipticity там где-то пропущено.
Константа эллиптичности 1.
Is a one.
Окей, хорошо.
Yeah.
Yeah, please.
Yeah. Then at this point we use the fact that okay, this is the integral where u is equal to t is essentially the perimeter of this set. The integral of where u is equal to t over 1 over gradient of u can be computed by using the coarea formula. So the perimeter is greater or equal than the quantity which I have shown before from the isoperimetric inequality. This is the measure of the set where u is greater than t. Here, a role is played by the fact that we are considering homogeneous boundary conditions. So the level set does not touch the boundary. And then by coarea formula, this quantity is essentially the derivative of this. So once we arrive to this...
У вас называется формула, по-моему, Кранрода. Он пишет коария, но...
Так, Юр, вот хватит уже, не по делу. Pardon, Ens.
Yeah. So from this, okay, now we have this. On the other hand, on the left-hand side, the integral where u is greater than t of f is less or equal than the integral between 0 and the mu u of t f star. This is the first property I've shown about the arrangements. And so finally, I end up with this inequality here. I would like to mention, just to go a little bit, that
one question more in the next slide.
Yeah.
Is this equality or inequality from the first and second?
From the first and the second here? Yeah, inequality because this is the perimeter. And this...
okay.
Perimeter.
It's perimeter, yeah.
Yeah.
And then in the denominator you have just equality.
Yeah, okay. This has to be made a little bit precise because you know, this set, if there are some level set where the measure of where u is equal to t is positive.
Yeah, but it is for almost
everything. Yeah, this is in equality.
Yeah. Okay. Thank you.
One has to check a little bit carefully these things, but it works.
Mm-hmm.
And so we arrive to this, and then at this point we have an inequality where there is only mu of u involved. And recalling that mu and u star were one the inverse function of the other, then from the inequality which I have shown before, minus u star prime is less or equal than this quantity. So if we put, roughly speaking, mu of t equal to s, then we can write down this. Now, if I go just a little bit before, in every passage, but wherever I have here made a passage, went from a line to another, I can immediately recognize that if u was already spherically symmetric and decreasing, all these inequalities were all equalities. So this means that the function v and its decreasing rearrangement solution of the function with the symmetric data, then this satisfies the equality here. And so this inequality here and this equality here allows us to get the comparison between U star and V star. So the idea is this. So I would say that the main points are to reduce everything to the symmetric case, and then to apply a suitable comparison principle between the solution of these two, the inequality here and the equality here. I would like to mention that there is a different approach which was introduced by Leonce in 81, where instead of using isoperimetric inequality, he uses a different method by using polyadzygo inequality. And so this is made because the integral where u is equal to t of grad u can be seen using qualia as the derivative of the integral where u is greater than t of grad u squared. So, being this a derivative, actually it comes out from a differential quotient, which can be written in this way. And so this can be seen as the integral of the energy of grad u squared of a truncation of u, because this integral is a computer where u is between t and t plus h. And so actually this means that this quantity here is greater or equal than minus t over the t of the integral where u sharp is greater than t or grad u sharp squared. So we have directly this inequality where only u sharp is involved, not anymore u, but directly u sharp without using isoperimetric inequality. So in some sense, the polyadzygo inequality let us arrive to a certain conclusion without isoperimetric inequality. And now
the polyadzygo is just based on the isoperimetric inequality itself.
Yeah, but it is not used in this passage.
Okay, agree.
No, this is a point because the problem is the fact that the gradient is constant on these level sets. And so if I use isoperimetric inequality in a different context does not work as in the local problem, in the local case.
Okay.
So this quantity depends only on u sharp. And so this can be explicitly computed, and it is nothing else. Okay, the gradient u sharp squared times the, okay, this quantity is like this. So there is the gradient of u sharp, is minus d over dr of u sharp. And then the integral over u equal to t, which is the perimeter. So
I'm sorry, it is perimeter or not?
The perimeter of a BR.
Okay, okay.
The perimeter of BR. And so this is essential. This is exactly the same inequality I got in the other way. Now, this kind of result have been obtained in many, many situations for elliptic equation with the lower order terms, for equation containing the P Laplacian operator, for equation containing the so-called pseudo P Laplacian. So pseudo P Laplacian, I mean an operator where there is a term uxi p to the minus 2 uxi, and here there is not the modulus. In the P Laplacian, usually there is the modulus here. So in this case, you have uxi to the power p minus 2 with derivative with respect to xi, which can be written down as the divergence of a certain h of grad u to the power p minus 1, h xi grad u, where h xi is equal to the sum of u xi to the power p and to the power 1 over p. And this kind of operators, they, in order to manage this one, one has to change the isoperimetric inequality which can be used, or the polyaxial inequality which has to be used, and it has to be used with respect to a suitable function of grad U.
It's anisotropic symmetrization, yeah?
Yeah, yes, this is an isotropic symmetrization, yes. Then it has used also for Monge-Ampère equation. I have to say that in the simplest case, you have to rearrange with respect to perimeters in this case. For problems with the Neumann boundary conditions, for parabolic equations, and so on. So I would like just to say a few things about the elliptic equations with the lower order terms and about parabolic equations, which are in some sense related. So I would like to say something about this kind of operator where C is greater or equal than 0. So I take a coefficient here which is greater or equal than 0. If I try to apply all the scheme I have shown before, one ends up with a symmetrized problem, which is written in this way, where the coefficient of V is G with sharp down, and the inequality is stated in terms of concentration. So one cannot prove that U star is less or equal than V star, but the integral of U star is less or equal than the integral of V star. And this comes from the fact that if I repeat the arguments for the case it's equal to 0 in this case, I end up with an inequality of this type. If C is equal to 0, this part there is not. If there is a C, there is a term where there is the integral of C times U, but on the left-hand side. So I have to go down, and in order to go down, I have to rearrange C and U in opposite ways. So I end up with this. Now, if I call capital U the integral of U star, and capital V the integral of V star, though where V star solves the symmetrized problem, I can write, and for simplicity, actually one can manage also the case where C is different from 1. So if suppose that C is equal to 1, the above inequality becomes an inequality in capital U, which can be written like the second derivative of U plus a coefficient times U less or equal, the right-hand side is exactly the same as the right-hand side I have got in the other situation. And obviously, for as concerns V, capital V, I have the same relation, but with the equality sign here. Now, from the comparison between these two, inequality and equality, gives us that capital U is less or equal than capital V, and so the integral of V star is less or equal than integral of V star. It is known and proved that this inequality cannot be improved to a pointwise estimate, because there are counterexamples. It is possible to see that in general does not hold that U star is less or equal than V star. However, in view of the property which I have shown before, if I have this inequality, then any norm of U can be majorated by any norm of V. This kind of result is useful also if one considers parabolic equations. For parabolic equation, the comparison is between the solution of this problem, the first problem, with the solution to the second problem, the symmetrized one, where F is substituted by F sharp. Now, F sharp is the symmetrization, kind of Steiner symmetrization of F, where T is fixed, and this symmetrization involves only the variable X. And also the datum, the initial datum is rearranged in a decreasing way. So, for parabolic equation, we have a result which is similar to the previous one, the integral with sharp of u star of sigma t di sigma is less or equal than the integral between 0 and s of v star sigma t di sigma. The reason for this is that a way to obtain this inequality is to discretize the elliptic problem and to consider this symmetrization scheme where you have now a problem which is independent of t, and you look for a solution ui to a problem on the left-hand side. There is minus delta and the positive constant times ui. So you can use the...
I'm sorry, maybe difference in там, Саш, перейди, там все-таки аппроксимировал, по-моему, производную первую, вот это, там наверху-то это УИ.
Нет, нет, Юр, ты не прав.
Не так.
Okay, please.
Okay, this optimal information can be used in order to study the summability of a solution, also in some limit case where one can successfully use spaces which are not the usual Lebesgue, but for example, Lorentz spaces. In some nonlinear equation, the existence is related to the fact that the norms of some coefficient has to be sufficiently small, and so these methods allow us to obtain the best condition. And finally, because of the fact that the equality case can be characterized, sometimes one can use these symmetrization methods also to prove symmetry properties of solution to problems with the symmetric data. So in the case of overdetermined problems. So the applications of these results are very, very large.
Sorry, can I ask a question?
Yeah.
A couple of slides ago about the low order perturbation. So what about if C is, say, a little bit less than 0?
No, if it is a 0, there is a problem. Okay.
Slightly smaller than 0.
An inequality. So you have to get a comparison between for this of this kind. So if you have this positive part, you go on the other side. So there is a problem of existence related to the eigenvalue. So if it is small, if it is not bigger than the first eigenvalue, you can still get this kind of inequality.
Oh, yeah.
So, and the symmetrized problem contains on the left-hand side also a minus C, which is this one, C minus to the power, to sharp, but with sharp up. So you have to rearrange in the decreasing way this part. So you have to rearrange in the increasing way the positive part, and in decreasing way the positive part, so that you build up an increasing function altogether.
I see. Thank you. Thanks.
You see?
Yep. Thanks.
And you still can do it, but you need to put some condition on the smallness of this negative part. Otherwise, it doesn't work.
Right. Thank you.
Now, the question which I would like to address, and I want to show some more recent results, concerns the symmetrization for non-local problems. So for non-local problems, I consider the simplest problem concerning the S Laplacian, the fractional Laplacian, and F can be taken suitably summable. The definition of S Laplacian is given here as the principal value of this integral. And if we consider a certain constant, which is written here, we can give a definition which is such that when S goes to 1, this goes to the Laplacian, to the usual Laplacian. So what can we say about this operator? About this operator, there are already some results. And the effect of symmetrization has been considered. For example, the first paper about this is by Di Blasi and Bolzoni in 2012. And these papers give some symmetrization results which are given in terms of mass concentration. So a little bit like in the parabolic case, or in the, I would say more like in the parabolic case for what I would say, because the approach to obtain a symmetrization result for this problem is to use an extension problem which says that the solution to problem 2 is obtained extending the problem to a local problem defined on an infinite cylinder. This kind of result goes back to a paper by Molchanov, Ostrovsky, and then more recently Caffarelli and Silvestre and other authors have studied the same kind of properties. Essentially, if W is a weak solution to this local problem, where here there is this divergence with respect to the variable x and y of this quantity equal to 0 in the cylinder C omega. C omega is omega times 0 plus infinity. W is 0 on, on the boundary of omega times 0 plus infinity. And this limit is equal to f, where this Ks is the constant which is written here. Then the trace of W on omega coincides with the solution U of the problem with the S Laplacian. So from this observation, one can think that using the Steiner symmetrization technique, which we have, which I have discussed about the parabolic problem, the parabolic equation.
And so it is problem on the plane, okay, on the plane.
No, this is on the cylinder. Omega is a subset of Rn. Okay, the cylinder, omega times 0 plus infinity.
How do you understand this solution? Пока не понимаю. How do you understand this solution?
Yeah, solution.
A weak solution, minimization of weighted Dirichlet integral. Так.
Yeah. So if we use the same methods which I have discussed about the parabolic case, actually not the same, not the discretization case, but other tools, then if we fix y and we symmetrize just with respect to x, we can estimate W in terms of the solution of the symmetrized problem with f substituted by f sharp. And so we get an inequality between solutions of minus delta SU equal to f and minus delta SV equal to f sharp. Okay, in 2021 with Bolzoni, we have obtained the same kind of result, but with a new method, which I would like to describe. And namely, we have proved the following, that if you solve this problem on the left, and V solves this problem on the right, then U is majorized by V, and the energy of U is less or equal than the energy of V. Here, U majorized by V means that there is a comparison of mass concentrations. So integral of V sharp is less trivial than the integral of V sharp. And this says that any norm of U can be estimated in terms of any norm of V. And so this is more or less what we have already seen. And as regards the energy in this fractional Lebesgue space, Sobolev space, is true. And this kind of inequality is also true for the local. Also, Talenti proved this result for the local problem. The main novelty in this inequality is not in this result is not resulted by itself, but in the fact that we use a completely new method, which is seems to be very flexible, and it is based on a Polyazzigo principle, which applies in very general situations. And I will concentrate on some extension which we have already obtained concerning the fractional Laplacian operator and the case of equation when the right-hand side depends on the unknown function. And I have to say that very recently, we have been able to treat with the same methods also the case of very general of the case where in the non-local operator, you have a very general kernel, which is not just 1 over x minus y to the power n plus 2s. Before going on, I would like to say that as in the case of the presence of a lower order term, the estimate which we get in terms of concentration cannot be improved as this example shows. So it is not possible in this context to obtain an inequality like the Talenti result, that U star is less trivial than V. And this comes out, for example, when you consider minus delta S of U equal to modulus of X in minus 1, 1, U equal to 0 on R minus omega. And then f of X is modulus of X. The rearrangement of f is 1 minus modulus of X, which is 1 minus of X. And then one can compute explicitly, can write down some integrals, which gives you the solution to this problem and to symmetrize the problem. And so if I denote by US the solution to the given problem corresponding to the choice of S with the blue line, the S with the purple line of the symmetrized one, here there are some plots of the solutions. This is the case where S equal 1/4, S equal to 1/2, S equal to 3/4, and then S equal to 1. S equal to 1 is the case of the Laplacian. And as you can see, the purple line is always above the blue line. So there is a pointwise estimate between the two solutions. While in the other cases, this does not hold true. So we suspect that there could be a threshold, a certain value of S, such that below there was no pointwise estimate, and above there was pointwise. But from this counterexample, it seemed we show that it is not possible to get pointwise for any S. The fact that close to 0, this was not the case. It was clear because when S goes to 0, Laplacian goes to the identity operator. So this solution tends to be equal to F. So naturally, it has to go somewhere. It has to go up with to be bigger than the solution of the symmetrized problem. So anyway, we have shown that also when S is very close to 1, there is always a level set of the blue line, which has a measure which is bigger than the level set, the corresponding level set of the purple line. So no hope to obtain a pointwise. So how to get this result? So the problem is that now, when you try to use isomeric, there is the possibility to use isoperimetric inequality. There exists some isoperimetric inequality for the S perimeter. One can define S perimeter, but when one does this in the Hardy-Littlewood inequality, in the Schwarz inequality, which one would like to use, then there is not equality in the case of the radial function. So we have thought to use a kind of Pauli-Azzigo principle in a certain way, as Leon's did in the local case. So we take this weak formulation of the problem. We use the test function phi of x as the function which is a truncation of u. This GTH is 0 if theta is less than t. It's theta minus t if theta is between t and t plus h. And the h is greater, and the function g is h when theta is greater than t plus h. We put it into the equation, and the aim is to prove that this integral, which is the same which was written before with the GTHU minus GTHU, y, is greater or equal than the corresponding quantity when u is substituted by u sharp. And in order to prove this inequality, which is a kind of Pauli-Azzigo inequality applied in the case of a local problem, we use the following representation, that this integral can be written as the integral between 0 and plus infinity times a certain constant of an integral I alpha times a power of alpha in the alpha. And this I alpha is nothing else than ux minus uy gth minus gth. And there is this exponential here, which is...
in fact, it is the integral representation for the kernel.
Yeah.
Mm-hmm.
Yeah. Because if you integrate this, you get just the kernel, mm-hmm. right? Mm-hmm. Because this power n plus 2 over 2 minus 1 gives you, this is a Gaussian.
Yeah. Mm-hmm.
Excuse me, no, with respect to alpha, it's an exponential. If you integrate this, you get the kernel. Yeah, mm-hmm. That's right. So, but now this is written in the same way as we have seen in the Ritz inequality. So there is here there is a function w with respect to x and y, which is already rearranged. It is already decreasing with respect to its argument. And then here there is this combination of uv, gth, gth. And so one has to show that I alpha is greater or equal than I alpha of u sharp. Now we use Ritz, the general rearrangement inequality, which I have shown before, with w equal to the exponential, a equal to 1, b equal to minus 1. And the function which we use is this f of u and v, u squared plus v squared minus u minus v, gth u minus gth v. One has just to show that this function satisfies the required assumption f, and then one applies, and one ends up with this inequality. So now on the left-hand side, you have everything which depends only on U sharp. So this quantity here is already symmetrized. There is only a symmetric function, a radial function. On the right-hand side, there is the integral of f times gth. And it is not difficult to show that this quantity here, once we divide by h and let h goes to 0, so we pass the limit as h goes to 0. On the right-hand side, we have the integral of f sharp. We can majorize. Here we majorize with the integral of f sharp. And on the left-hand side, all what is written before can be written in terms of a double integral of u sharp minus u sharp times a certain function theta, which is the integral, which is the angular, everything is radial, so you have to integral only under angular variables. And this quantity can be written down as an hypergeometric, and a combination of hypergeometric functions, which are written here. So this is very standard computation once you know that U is radial. So now there is the last point. We have this inequality where there is involved a symmetric function. Now, for the solution of the symmetric problem, you will have V instead of this U sharp and equality here. Now, can we state a comparison between U sharp and V? So this was not so easy. In the case of the local problem, there was no problem. It was just a first order or second order equation with respect to the unknown variable. So here we have observed the following. If we denote by capital U, not the concentration, but the spherical mean function. So we take the mean of U sharp on a ball of radius x. And we have shown by using a formula contained in a paper by Ferrari and Verbisky concerning the calculation of the S Laplacian computed on radial function, that actually all that quantity which I have written before, which is here, can be written as r to the power n times the Laplace, the S Laplacian, computed on capital U, but computed as if the number of variables are not n, but n plus 2. So this means that all the inequality which I have written before reads as this one. So that minus S Laplacian of an n plus 2 variable of capital U is less or equal than this quantity on the right. Then for V, we have the same with equality. V is the spherical mean as before. And then from these two, equality and equality, inequality and equality, we end up with this concentration, U less or equal than V. So in terms of what I have written before, this means that U is majorized by V in terms of concentration. Just a word about the idea of writing this quantity as an S Laplacian n plus 2 dimension. The idea came from the fact that actually this double integral can be seen as the integral of a ball over a ball of minus Laplacian of U sharp. Oh, there is sharp here, which is the integral of BR of this quantity here. So if one uses formally, if one uses the representation via Fourier transform of the S Laplacian, The S Laplacian of U sharp, in a formula contained in paper by Garofalo, can be written as a double integral involving U sharp, obviously, but also the Bessel functions, Jn over 2 minus 1, Jn over 2 minus 1. So if I integrate this, I mean that I have integrated all this, and then I can use the recursive formula concerning the derivative, which is written here, in order to show that integrating between 0 and r the S Laplacian, this integral goes inside and comes out to be the same quantity, but instead of n minus 2, n over 2 minus 1, there is n over 2. Instead of n minus 2 minus 1, n over 2. And here, instead of n over 2, there is n over 2 plus 1. So essentially, it's the same quantity, but with in n plus 2 variables. And so this justifies, at least formally, that formula. So just a final remark concerning this is how can we recover the case S equal to 1? So if I write down minus delta in R n plus 2 capital U less or equal to minus delta R n plus 2 capital B, this inequality comes when we let S goes to 1. So if S goes to 1, in the local case, we have this inequality. And this inequality, if one computes the Laplacian with respect to n plus 2 variable or capital U, this quantity is just U sharp prime of R. So we end up with the same inequality which you have seen before in the proof of the result of Talenti. So this concludes the part which of the discussion about the S Laplacian. Now I would like to have the time, the last 15 minutes, I would like to say something about possible application of these methods, for example, to the SP Laplacian, so the fractional P Laplacian, minus delta PSU equal to F, which is defined according to a definition given, for example, in the case of Gomez Castro Vasquez, as the principal value of ux minus uy to the power p minus 2 times ux minus uy divided by x minus y to n plus sp. Now there is this p, which was 2 in the previous definition, with this constant. Well, we have observed that if we use the same test function, we end up with the same integral as before. Here there is n plus sp. Here there is this power to the power p minus 2. And one can use the same argument based on Albrecht-Lieb inequality, but only for p greater or equal than 2, to say that the first inequality, which I have shown, holds true also in this case. So here, for p greater or equal than 2, you say that this integral is greater or equal than the other integral where u is substituted by u sharp. And then in a paper in discrete and continuous dynamical system with Bruno Bolzone, we have proven that we can find a suitable, which is not optimal. Actually, we think that one can do better. There is a comparison problem with a problem which is not does not have on the right hand side the rearrangement of f, but another function which is defined here. Anyway,
excuse me, is here just minus p fractional p Laplacian?
No, this is a Laplacian.
Laplacian?
Yeah, and there is here the g, you see, there are some powers. So this is a with respect to the problem is not the same. So it's not the same. You just can say that U sharp is controlled by V, and the function which is on the right hand side is not it's not like F. There is some 1 over P minus 1 here. It's not okay. The only thing which is good is that we can recover some estimate on the solution U using this problem, which in some cases are optimal, but not in all the cases. This is not yet satisfactory. This is just you know, a first step. We would like to find delta PS here and here F sharp, but here we were forced to use isoperimetric inequality at a certain point. So here what is missing is the good comparison result, which we were not able to find. Or also, we have considered a problem like this, which has been already considered in the case of local operators. So problems with singularity, where on the right hand side there is u to the power gamma, where gamma is greater than 0, and f is a positive function belonging to L infinity. Now, this problem has been considered in many papers. The first papers, this by Crandall, Rabinowitz, Lazer, McKenna, Kawol, Boccardo, Orsina, they are all papers where the existence and properties of solution of these problems have been considered.
Even for fractional Laplacian?
No, this for the first 4 paper for the Laplacian.
Okay.
The local one. Then Brandolini, Chiacchio, Trombetti gave some result about symmetrization for the local case. And Barrios, De Bonis, Medina, Perar have studied this problem for the S Laplacian, but not symmetrization results. So the only paper among this about this problem is the last one, Barrios, De Bonis, Medina, Perar. So the idea is to see if there is a comparison problem for this one. And the natural problem is the problem, here you need to have F bounded for, in order to let the
One moment.
the method work.
Gamma.
Gamma is positive.
And O, so only.
Only?
Yeah.
Gamma only positive, I mean.
Only, okay.
Yeah.
Только, да, только.
Ну да, конечно.
Like no upper bound.
Поставить любой степень вообще. Ну ладно, хорошо.
No upper bound.
No upper bound for gamma. Okay.
No.
Надо решение понимать, хрен его знает. Ну хорошо, не знаю.
Okay.
Well,
in a paper with De Bonis, Brandolini, and Bolzone, we have studied this problem, and we have proved that if f is bounded greater or equal than 0, if I take a solution of this problem, the solution of this problem, and the solution of this other problem, then U is majorized by V in the sense which I have discussed.
Okay, one moment. How you understand solution for any...
Так, Юр, стоп. Времени уже нет, извини.
Okay, I
Uh-huh.
I am considering weak solution in a sense which I don't want to get in. I mean, one has to suppose something which treats the fact that this can go to 0 on the boundary. Okay. but I don't want to discuss the existence of solution. I can tell you that in the paper I quoted, there are results about the existence. And one can apply the same arguments to arrive to this inequality here. So there is the same quantity on the left-hand side. On the right-hand side, there is a certain constant where you can put the norm of f in L infinity and various constants which come from the computation. And there is 1 over u sharp to the power gamma integrated. For the symmetrized problem, we have the same inequality, but with the equality sign. And so once again, one has to give an argument to say that u sharp, u is majorized by v. And so in this context, the argument which I have used before cannot, at least we have not been able to use it. And so we needed a new argument in order to obtain a comparison between u sharp and v. And this argument comes from the following lemma, which says that suppose that u and v are non-negative continuous function on 0R, such that the following integrals are well defined. And suppose that h, that here there is the integral between 0 and r of u rho. HV is the same integral of v, and suppose that h of u, hu minus hv admits a positive maximum point in a certain point r bar. That is, if I compute h of u in r bar minus h of v in r bar, this is positive, and this corresponds to the maximum of this quantity. Yeah? Then every time I have a positive increasing function h here, if I compute the integral between 0 and r bar of u rho times h, and the integral between 0 and r bar of v rho times h, then this difference is positive. So an analogous result, but with all inequality reversed, hold true for the function ku, which is the integral u between r and capital R, and kv between r and capital R. So once we have this lemma, we go back to this difference, and if r bar is a positive maximum point for h of u minus hv, we have that using the fact that theta has the right right monotonicity, the difference between these two integrals is greater than 0. Vice versa, from the other side, the difference between these two integrals has the opposite sign, obtaining the contradiction. So this means that hu minus hv cannot have a maximum point, so this is always less or equal than 0. And so being always less or equal than 0, if I recall the definition, this means that u is majorized by v. In the local case, a similar result was obtained in the form u to the power gamma majorized by v to the power gamma. And when gamma is between 0 and 1, the result obtained in the local case is a little bit better than the result obtained in the case of the fractional Laplacian. But this can be understood because in the S Laplacian, the minimal comparison concerns U majorized by B. So it's not possible to go below 1. And finally, I have also to say that if F is just nil 1, if I don't want to save the structure of the operator of the equation, sorry, one can state also a comparison of the solution of the original problems in terms of the solution of this problem, where there is not anymore a singular term, but there is this term gamma plus 1. And the comparison is not between U sharp and V sharp, but between U sharp to the power gamma plus 1 and V sharp, solution of this equation. And this comes from the fact that our equation, if we multiply by U to the power gamma, essentially, okay, this is we end up with a problem which is written in this form, plus a term which has a sign which can be thrown away. So this is all. I think that I am just on time. And I would like to thank you for the attention.
Okay, thank you. Please, questions or comments?
Саш, пожалуйста, переведи ему.
Да.
Доклад замечательный. Там вот до конца писал. Меня интересует вот что. Он ученик Джорджа или нет? Вот спроси его. Мужик такой, ну, старорежимный. Спроси его.
Что спросить-то?
Он ученик Джорджа или нет? Вообще
Нет.
доклад замечательный. А он ученик Джорджа или нет?
Нет. Okay.
Нет?
Okay.
Спроси, вот вопрос
I
я
don't
задал.
understand.
Yeah. Okay. Are you were you a student of the Georgia?
Excuse me?
Were you a student of the Georgia?
No, I was not a student of the church. I was a student of Trombetti and Albino here in Naples, which were started
Нет,
this.
получается, да?
Okay, I would say I am more a student of Talenti in some sense.
А, Таленте? Окей.
Yeah, Talenti.
Спасибо, Саш.
Okay. I have a question. Not a question, but a request. You said that the sharp constant in or reduction of the problem of sharp constant in the Sobolev inequality was made in 3 papers. I know only 2 of them, Oben and Talenti.
Yeah, Oben and Talenti is also this Ilden paper.
Okay, can you send either...
I can send you a copy of this.
Okay, great, great.
Yeah. I should have one. So the Ilden paper, I will.
Yeah, thank you. It's very interesting. More questions or comments?
I have a question. If we have integration non-local operator instead of power f Laplacian, we have an operator with a kernel which has finite second moment in the vicinity of 0. That's generalization of
yeah, there are some
Laplacian.
generalization. We have okay, we have just recently got some results. For sure, in the case where the kernel is L1. So everything works for L1, but actually it seems to work when you suppose that if you multiply the kernel times the maximum between 1 and x squared, and the integral is summable, then also works. But we have more concentrated on the case of the singularity closer to the origin. We are taking everything in a bound set, so we don't care a lot about the summability at infinity.
Yeah, sure.
So there are some results in this direction. We are just completing to write it. So, but
I see.
I
So
don't know
it-
if you did say the second moment. Yeah, it should work also in this case. So when you multiply x squared times the kernel.
Yes,
Yeah.
it should be integrable. Yeah, that's
Yeah,
the
yeah,
meaning.
yeah,
Yeah,
yeah.
in the vicinity of zero. Indeed, we don't care much about the
Yeah,
behavior
yeah,
at infinity,
yeah.
but
Okay, we are completing. I think that it works also in this case. I cannot say it works because we have not completed the computation explicitly. So, but L1 works. So
Okay.
if the kernel is in L1, okay.
Mhm.
Okay, let's thank the speaker again.
Okay, thank you.